Out of the tank, we've got a line here, and we're going to put a meter in it right there. If this has got a pressure on it from a pump or whatever, it goes through that meter. When we lower the pressure on this side, if there's any gas, what's it going to do to that turbine meter? It's going to make it spin faster. So we'd like to keep that pressure from flashing gas out in our meter, giving us a false reading. So we want our meter then to be upstream of a control valve. So here's our control valve controlling rate. We want to try to hold that back pressure on that meter so that we can go through it without flashing. Here's a typical hookup for a master meter. This is our meter that's in the main line, built with a bypass around it. You always want to consider maintenance in anything that you build or construct. At some point, it will break. If it's a mechanical part, it's going to have to be repaired or replaced. And so providing this bypass around here gives you that ability to repair or replace those meters. And our master meters especially need that kind of construction. On the injection manifold, this would be a typical hookup. If I'm looking at a manifold, it's a big piece of pipe, and I've got smaller pipe running out of it. I'm looking down the end of this. This is generally, say, a 4-inch pipe, and these may be 1-inch injection lines running out of here. Come through shutoff valves, a strainer, catch the solids, the meter, and then that flow choke or that control valve to hold the back pressure on this meter. We'll look a little bit at the components. These are special chokes that are used in most water flood applications. They're a variable orifice. You got one plate that has fixed full open holes in it. You got a second plate that when it's full open, those holes align. And then as you adjust the rate, you bring the holes further or closer or further apart, and it introduces a variable rate through there where it can be fully closed, the holes aren't aligned, or it can be fully opened where the holes align through there. But it's a real simple choke. It's relatively inexpensive. It's nothing like the choke we've been talking about where you're on a high pressure wellhead controlling high pressure gas rates. That particular one is made by Taylor. These are simple Y strainers. Flow goes through this way, so as it's coming in here, flow actually goes down through this cartridge and then out. This cartridge catches all the solids and junk. It's got an easy clean out port on it, simple to maintain. One installation went out and checked, and the pumpers had pulled all of these screens out of these strainers upstream of the meters. Asked them why, they said, well, they kept plugging up. And that's exactly what they're supposed to do, is catch that solids material that's coming down the line. But if it makes a headache for them, they're going to make life easy. So as an engineer, what do you do about that? You got to explain why it's important, but what else is it telling you? You're not doing a good job cleaning up your water because you're putting all this junk down this line. So I've got another problem I need to address that's bigger than just keeping the guys in the field happy. But they will find a way to make it easier, I guarantee you. Been there, done that. The turbine meters that are commonly used, I think you've seen these before, just have a rotor that spins as proportionate to the volume of fluid coming through. These are really easy to design. The design hasn't changed much in the last 50 years. This is for one particular manufacturer, and most all their curves are the same. For this 1-inch meter, if we look at how many barrels a day we want to measure, This one, for example, has a 10-to-1 turn down. You can go as low as 170, as high as 1,700 barrels a day. And there are design curves that show the pressure drop. This is pressure drop plotted versus flow rate. I took this curve out of the sales literature for this turbine meter manufacturer and compared it to the same curves I was using when I was just out of school in about 72 or 73. It's exactly the same curves. They haven't done anything to change this pressure drop through these turbine meters, because they're just pretty simple, reliable. Here's that 1-inch meter that we were looking at, and it's got that 10-to-1 ratio on it. You always need to be aware that meters have a lower end on them where they become inaccurate, if you will. The reliability and rangeability is not the same. And then at the higher rates, the pressure drops become pretty significant. But at 1 PSI, I'm still able to measure about 10 gallons a minute, over 300 barrels a day, with negligible pressure drop in the system. Wells and wellheads. We go to put that water flood pattern in. Are we going to use the wells that are already there? Would you? Or you just drill new injection wells? You're probably going to have a combination of both. Drilling new wells, you should have all the techniques now to get a good well in place. It's going to be serviceable to you. But what if you go to that old well? You've got to make it part of this system now. We've got to look closely at the condition of the casing. Are the perforations in zone? Do we have to do things to modify that to where we get good water flood conformance? Are the perforations plugged up? Just over time, those have a tendency to do that. So we need to look at wellbore cleanup. So the well needs to be considered as much a part of the facility system as anything else. It's not really a completions problem, it's more a facility problem. A wellhead hookup, after it's come off the header, our header is back here. Here's our individual line going up. It will have a ball valve, a check valve, a wire line cap, pressure gauges, and sampling ports on it. Sampling ports are important through the entire system. You're always going to wonder, what's my water quality at any given point? Is there anything changing? You know, it's more solids at one portion of the wellhead than anywhere else. And so this piece and this design right here, some of those are made as interval units, but again, you need to have a hand in there in designing that, what that looks like. On the water injection wells, there's some things you need to think about if I go in later. One of those, if I have some perforations down here and I'm setting my packer, I'd like to leave an interval of about a 50 to 100 foot unperforated pipe section below that packer. And the reason is, if I'm going in here with wireline, one of the tests that we like to run is a spinner survey. And if we want to see how much injection the perfs are taking, we run that spinner survey tool in here with the well injecting, and we measure how fast it's turning. And as we go by perforations, if it turns faster in one area than it does in another area, you get relative rates of injection with that spinner survey. If I've got this 50 or 100 foot section here of blank pipe, no perforations taking injection, I can kind of calibrate my tool. I can stop right in here, see what it looks like in blank pipe. Then I can go down and run my test and get a good reading on the spinner survey. The packer obviously needs to be set inside a C-minute interval. If I don't bring my C-minute high enough, it's got to be there. Internal lining on tubing. Entrained gas can be a real problem on some forms of plastic lined tubing. It'll actually penetrate the tubing and cause it to pop apart from the steel walls. You've got to be careful and check for that. This packer, the wetted parts of it, on injection wells, we need to make sure we've got either the right metallurgy Our packers can be internally plastic coated too, to keep them from corroding. And then finally, cathodic protection to prevent surface problems with our electrolysis. One thing that's come into vogue more recently, especially in the areas where we're producing lots of water. And when we say lots of water, a typical shale well produces 3 to 4 barrels of water for every barrel of oil. And back to the Permian again, right now there's 3.5 million barrels of oil being produced every day. Think how many millions of barrels of water it is. I got my water bill from the city of Lubbock and looked at they had statistics on it on how much water the city of Lubbock uses in a given year, fresh water. I took a look at 1 year of produced water from the Permian Basin and said if I could treat all that produced water and make it fresh water, it would run the city of Lubbock 18 years. So that's a big, big number. And somebody's going to jump on those kind of statistics and say, you need to be cleaning it up, you know. The hard part about cleaning it up and getting it is getting it all in one place. And that's where these midstream water companies are coming into play to gather water and collect it to where it can be consolidated in one spot. How many thousands of wells are there in the Permian Basin? 20 to 30,000. And so we look at that many wells, and how many collection points is that? A lot of them are old single well batteries. We're seeing a lot of batteries that are a lot bigger, that have a lot of tankage, a lot of accumulation at one point. But how do we get all that water together? So this was one operator that did this system. But this is typical of what a midstream company is coming in to do. We understood midstream companies when they were doing gas. They gathered gas and they brought it together from individual sales points and took it to plants. And now people are coming in and doing this with water. The thing is with water, these are big, big systems. These frac ponds that are placed out here, these are 500,000 barrels each, generally. Really important. So on these frac ponds, those are 500,000 barrels each. That's about one frac job sitting right there. There's 466 rigs running in the Permian Basin right now. So multiply that by however many frac crews are down there working. That's how much water has got to be moved. So the midstream companies are coming in, they're building these frac ponds, they're doing the infrastructure, laying down these roads with big inch pipe to bring this stuff together. This is 36-inch diameter poly pipe. Most of the poly pipe that's used in oil field gathering systems is 2-inch to 3-inch. It works great. It doesn't need to be G-rated for the hydrocarbon to go through it, but in these water systems, these are 20, 25-foot joints, maybe 30 based on those trucks. A 36-inch poly pipe connecting all these systems together. You can see what size of trencher it takes just to get that stuff in the ground. So the midstream companies are saying to the operators, we'll take this investment on, we'll take your water, and then she needs it over here. So I'll handle your water for you, get rid of it. It's a waste stream now, you don't really want it. But then I'll sell it to her. And I'll do all the interconnected piping to get it from there to there. You're happy you got rid of your water, right? You don't have to mess with it. You're happy you need it. Can't drill enough freshwater wells to fill up my 500,000 barrel tanks that I need. So that's their business model. that they're basing all this on. They have to do a certain amount of retreating to take your dirty water and make it clean enough for her to inject. They're taking that cost on. They're not treating every barrel. So these water midstream companies are not only looking for distribution, they're looking to set up disposal systems as well. They recognize that, by the way, for every one of those treatment systems that we looked at that takes water down and makes it better, fresher to use, there's a waste stream associated with that. We don't magically burn off all of those contaminants, those solids. They've got to be disposed of. So this is the purpose of a midstream company. These are some of the pumps typically involved with that. They'll back up these trailers, whichever pond's being needed, put it in the main pipeline, move it down, and then in some cases they're building these permanent injection stations to move lots of water through central parks. Those are can-type centrifugal pumps. They're much like the pumps used in irrigation systems, just several hundred times larger. Okay, any questions about handling water? Injection stations, SWDs, treating? None? Yeah. I'll see you on senior design, we'll see. So there's been a lot of questions asked about how many tanks do I need and what's a reasonable number to use. And the question about tanks, notice I didn't say how many oil tanks or how many water tanks, and what does it cost. So I'll give you answers to some of this that you'll like, some of it you won't. But I want you to think about it based on a couple of examples here. So how many do I need? This is in the Sahara Desert. It's in Tunisia. The field is a 4-hour drive off the blacktop to get to it. The jumping off spot is Tatooine. If you're a Star Wars fan, that's where the name came from. So it's 4 hours off the blacktop through the desert to, see, we set up field camps to house the workers while they're out here. There's a rate of 25,000 barrels of oil a day. We were able to tap into a line that ran from Algeria up to the coast of the Mediterranean, which tied into another line under the Mediterranean to take it on to Europe. So the first solution was we had a first oil date to meet. We had to get the oil out of there. That was all the project economics, all the Wall Street expectations were that this oil was going to flow on that day. So we knew we had high volumes to lift. We put in 40 tanks, each one of 500 barrels a day capacity. So that gave us 20,000 barrels a day of storage. That meant every day we were going to these tanks, gauging the tank, metering it, or not metering, just gauging it, running it into the pipeline. Just opening it up to the pipeline, it would go to the pipeline suction pumps that would take it on. How many leak points do I have there? Look at this, all this piping that connects all this together, all the walkways, all the maintenance that goes with that. That was 40 tanks put together. As the more and more tanks you put out there, these problems multiply significantly. So the solution is to build bigger tanks. That's easy. These tanks that I showed you here, get back on. Each one of those is one truckload. They can put it on a semi, bring it to the desert, and we were able to get 40 of them. I think we stopped there because that's just about they're all were in country available to us. So that's one truckload. A 1,000-barrel tank, usually about the maximum you can put on a truck. So the solution is to build bigger tanks, right? And this is, again, back to the Aggies. I just can't get off of this. They were selling watermelons. And they had a booming business. They'd run to Arkansas and buy them, and they'd bring them back to A&M and sell them. And the deal was they were going up to Arkansas and they were buying them for $1 a piece, bringing them back to A&M, selling them for 50 cents a piece. So they decided they were losing money. And they had this Aggie economist look at the deal. And he said, he looked at this system they had. They could go to Arkansas, they get them for $1 a piece, bring them back to College Station, they sell them for 50 cents a piece. The answer was simple. He said, get a bigger truck. So the solution sounds simple, doesn't it? Let's just build a bigger tank. So to do that, here's what's involved. First you lay out the foundation of the tank, and then you start constructing, bringing in sheet steel pre-bent for all of these staves. Build them together. You're working on scaffolding. And again, remember, it's 4 hours back to a doctor. We actually had a doctor in camp. But this is a typical construction of a field tank for 30,000 barrels. And so you build 2 of them. One would take care of 1 day's production. While we're running it, we're filling this one up. So do I need 1 day or 2 days or 3 days of spare capacity in case I have a pipeline problem? Sounds simple, doesn't it? But the reason we rushed to get all of these out there was to meet that production. We were drilling wells, we were completing them, we had the production volumes to go. So this satisfied that early requirement. This was a permanent solution. And making even a call on a 30,000 barrel, or 25 or 30,000 barrel a day stream was, we'll back it up with 1 day. Do what?
So number of tanks is enough for just you want to have about a day's worth?
If my well makes 10 barrels a day and I got a 400 barrel tank, I'm in good shape, right? What if it makes 100 barrels a day? Yeah. What if I make, say, a typical battery runs about 25,000 barrels a day? Because okay, this is Tunisia, say it's kind of far-fetched. Let's go past it. There. That's just south of Midland. That's a battery handling about, I believe, 10 or 15,000 barrels a day. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 2. There's 20 tanks. 2,500 barrel tanks. 10,000 barrels a day. They're just barely holding 1 day, aren't they? So what's the right answer? You tell me. Tell me what business risk you want to take, what total volume is involved. What, as I put more and more tanks here, I'm doing all the same things I did in the desert in Tunisia. It was a long way to get to them. Even though these are closer, I'm still having those same connection, leakage, gauging, all those other problems, although I can put this on LAC unit. By the way, in Tunisia, we built the LAC unit. It was the first one in the country. And so the national governmental organization we were dealing with wasn't really too sure how well that would work. And so we said, okay, so if there are uncertainties about the meters, we'll put a meter on it. We'll put a single meter, Coriolis meter, to measure that volume, and then we'll put it in series, another Coriolis meter. One of them fails, we got this one going. And then they say, well, we're not, you know, we're still not really certain. Say, okay, we'll do another loop. We'll put 4 meters on it. You can go through one side and both fail, we'll switch to the other side. We put 4 Coriolis meters on a meter skid. It costs just a little under $1 million for a light unit. Never ran a barrel through it. Because of the unfamiliarity and the uncertainty of that technique of selling oil in that particular location. So what's my business risk? You've got to answer that question. I can't tell you what it costs to build those fuel tanks. I think you can see though from what has to be done, the manual labor, the construction, all those kind of things that have to go be put together to get a tank built. The time element, we satisfied the time element by doing the blue tanks in those previous pictures. The blue tanks satisfied our immediate need. We could truck those out there and hook them up as we grew. This satisfied the field construction satisfied a longer term need. So on your design, you're going to have to make some business decisions about what you want to do. Just remember, as you grow this field right here, the maintenance and logistical problems grow proportionally with it. Are there any other questions about anything long here? Okay. Okay.
Do you not have any questions about the facility design?
What kind of pump would be used to move water from your facility?
Probably a centrifugal, but you're not having a high enough pressure that a centrifugal can't handle it.
More question for him? Just today, right? He's here. Don't have any question, are you sure? Alright, let's move on to the pipe calculation, equivalent length. Okay. You already know about water treating, okay, and a little bit more about tank. Okay. Now it's about pipe. We put pipe, and this time it's about the concept of equivalent length. Okay. A short pipe of 1 inch, 100 feet, is equivalent to 3-inch pipe that is a lot longer. Okay. In row, what is that? The pressure drop is the same. Okay. In a short pipe, smaller diameter is have the same pressure drop as a larger diameter that is longer. Okay. Both of them has the same pressure drop. This is equivalent length for the gas pipeline. Okay. The formula to do the calculation is matter. Okay. This time I use this formula. Okay. This is the formula from the last time. Okay. When you use both formula, I have flow rate equal to all these things. I put the number in. Look at this. To 5,280. Okay, next in row. Array, what is that? 5,000 for feet to mile? Okay, it is. Okay, so 5,280 feet equal to 1 mile. We have 100 feet, and we know that it is 1 inch. Okay, I put the number over there, and then I will get that that is the flow rate. Okay, the flow rate is x. Okay, I will get that P1 squared minus P2 squared. That is kind of pressure drop, right? So this is the first equation. This is how I calculate the equivalent length for the gas pipeline. Equation 2, I have same thing flow rate equal to some constant over there, and P1 square minus P2 square. This time I know the diameter, which is 3 inch. I put 3 over there, but I don't know the equivalent length. I know that it just has to be longer. Pipe A is that short, but pipe B has to be longer so that it has the same pressure drop. So I put the unknown to be Z. Okay, that is Z. Next step, I use equation 1 divided by equation 2. Do the math. I get Z equal to that many feet. Alright? So this means equivalent length can be calculated. So equivalent length that allows the same pressure drop can be calculated, and the answer is dependent upon which equation that I use. Alright? If I use panhandle B, I get one answer. If I use isothermal case, I have another answer. Alright? So last time we go through this, what we have is two concepts. Equivalent length, okay? Let me repeat a little bit. We have 100 feet, 1 inch. What is the equivalent length in terms of 3-inch pipe diameter? So it has to be longer than 100 feet, right? What about equivalent diameter? If I have gas pipeline that is 33,000 feet, 3 inch, what is the equivalent diameter in terms of pipe, or what is the equivalent diameter of this pipeline in terms of 100 feet? See this equivalent diameter? We know that it's 1 inch because we know that it produces the same pressure drop. But intuitively, can you tell whether it's going to be more or less than 3 inch? Can you? Okay. What if this is 33,000 feet, 3 inch ID? Okay. I change the question. Okay. Instead of 100 feet, I change to be 1,000 feet. What is the equivalent length diameter of this pipeline in terms of 1,000 feet? Is that going to be more than 1 inch or less than 1 inch?
You're asking what diameter pipe?
Equivalent diameter. That diameter, that if it is that long, it will produce the same pressure drop as that.
Right. So the pressure drop's the same. The variable is what diameter pipe.
Yes. That yes. Okay, Daniel? Is Daniel or Dennis? Daniel? Is it more than 1 inch or less than 1 inch?
It's more than 1 inch, but less than 3 inch.
More than 1 inch, but less than 3 inch. So if that number becomes 33,000, then it will become 3 inch, right? Okay. So make sure that you can tell whether it's the equivalent length is longer than a certain length or shorter than a certain length. You can just answer right away. Okay. This is the calculation. If I use isothermal equation, this is isothermal equation taken from previous lecture. Flow rate is standard cubic foot per day equal to a coefficient multiplied by 1 over square root f, okay, and have all these formulas. What I pay attention on is this L, okay, that is the length in mind, okay. The way that I get the equivalent length, I say, okay, pipe A, I know the diameter, which is the dA. I know the length, which is LA. Pipe B, I know the diameter, which is dB. The equivalent length is L sub E. Do the math means do the ratio. Equation 1 divided by equation 2. So all these things cancel. The term that is about friction factor is not that cancel, but it stays over there, okay? And eventually, do some math, I get equivalent length equal to length of pipe A multiplied by this formula. That's it. That's how I get equivalent length by using isothermal equation. Can you do it in the exam? No problem, right? Okay, this is isothermal equation. Equivalent diameter is derived the same way. Pipe A, I know the diameter, I know the length. Pipe B, I assume that I know the length, but I don't know the diameter. The diameter is equivalent diameter. Do the ratio and some rearrange, I get formula for equivalent diameter. Okay, this is based on isothermal case. Okay, and you do that. Yes, as long as you write it in, right? This is isothermal equation. Weymouth equation is just different constant and different exponents. Most of the stuff is the same, so I have two equations. Do the ratio, rearrange it, I get another formula. And this is a formula to get equivalent length for Weymouth equation. Equivalent diameter for Weymouth equation. It's that easy. Right? I did the math for you. I derived it. But this is, we have two pipes. If I know diameter and length of pipe 1, I know diameter of pipe 2, how long should be pipe 2 to make the same pressure drop as in the case of pipe 1. So this is how we do it. Okay, make sure you can do it. Handle B, same thing. Okay, do the ratio, get the new formula. This is formula for equivalent length and equivalent diameter. Okay, your job is what? Have this equation and the final result for equivalent length, equivalent diameter. Okay, very easy, right? Just write something in and be able to do the exam. Okay, summary. Formula for equivalent length, equivalent diameter for the case of gas pipeline can be written as this in summary. Okay. Notice that for isothermal case, I use friction factor. Okay, friction factor stay there. I will need to know epsilon, okay, the roughness, or if the roughness stay the same or not. It should stay the same. Okay, here's the formula. Let's do something. 1 inch pipe and 100 feet. Okay. For this pipe, what is the equivalent diameter in terms of 500 feet? So I have another pipe, 500 feet. What is the equivalent diameter to have the same pressure drop as in that case? Is it going to be larger than 1 inch or smaller than 1 inch so that you have the same pressure drop? Larger. Who? Just 2, 3 of you that is larger? Larger. What about smaller? Smaller. No one? Stephanie? Larger or smaller? Larger. Luis Rodriguez? What's your name? David? Larger or smaller? Larger? Let's take a look at this one. So I have a pipe, 1 inch, 100 feet. Okay. If another pipe is 500 feet, which is longer, to have the same pressure drop, it has to be larger than 1 inch. Right? Good? Memorize this picture. Okay. Next is about the series pipe put in series. Okay, and parallel. The way that we do pipe put in series. Okay, for Weymouth equation, I rearrange it in terms of pressure drop for each of them. Okay, this is pipe in series. I know that total pressure drop is the pressure drop of each part added together. Okay, then I rearrange it, do the math, I get this formula. This is pipe in series. Okay, pipe in parallel, I know that the flow rate is the same. Okay, total flow rate, the flow rate is not the same. Total flow rate is the summation of each flow rate. I add those equations together, rearrange it, I get another formula. Okay, this is the formula for that you have to write down. Pipe put in parallel and pipe in series. It is derived based on Weymouth equation. If we use other equation, you get other value, okay? So what about the loop pipe? Put it in parallel first, and then put in series, use two equations, mix them together, we are done. Okay? Good? Alright, see you next time when we review the loop pipe. Do we, anyone haven't submitted the release form? Do we have class next Tuesday?